starting to build the complex numbers. We've learnt that we can't square root negative numbers. However, what we're going to do is introduce you to complex numbers, which allows us to square root negative numbers by introducing a new concept, which is real and imaginary numbers. So real numbers come from the real number set. Imaginary numbers come from the complex number plane, which includes imaginary numbers. Here, if we have the square root of -1, we let that equal I, which is our imaginary number. The set of complex numbers is C. The real number system is R. R is a subset of C. All real numbers are part of the complex number plane. Okay, so if we know that I is -1, which we have here, we know that I squared is the square root of -1 squared. If we square and square root something, we just end up with that something, which in this case is -1. I cubed is the same as -1, I squared from up here, times the square root of -1, which is -I. And I to the power of 4 is -1 to the power of 4. That's the same as -1 square rooted and squared times -1 square rooted and squared, which is -1 times -1, which is 1. From this, it follows if you want to evaluate something like I to the power of 5, I to the power of 5 is I to the power of 4 times I, but we know that I to the power of 4 is 1. So I to the power of 5 is 1 times I, which is I. When I have something like this, basically what I do is I find the remainder after I divide by 4. For instance, if I had I to the power of 23, how many 4s go into 23? 5 do, with a remainder of 3. So I to the 23 is exactly the same as I to the 3. We know that I to the 3 is -I. So I to the 23 is the same as I to the 3, which is the same as -I. If I had I to the 51, how many 4s go into 51? We know that 12 4s are 48, so I've got a remainder of 3. So I to the 51 is the same as I to the 3, which is -I. So you always just divide your index by 4 and see what the remainder is, and then you can evaluate the remainder. The remainder is either going to be 1, 2, 3, it won't be 4. The reason being is that when you divide by 4, if it fits perfectly, you're going to have no remainder. The real part of a complex number is the part that doesn't have an I. So in this case, with this complex number, our real part is the x. Our imaginary part is the yi. So the real part of z is x, and it's given by the real part of z. The imaginary part of z is y, and it's given by the imaginary part of z. So if I wanted the real part of 5 minus 3i, the real part of 5 minus 3i, the only part that I want is this part, because I don't want the imaginary part. So the real part of 5 minus 3i is just 5. If I want the imaginary part of z, I want the imaginary part of 5 minus 3i. My imaginary part is just -3. If I want the real part of z, we know that that's 5 from part A, minus the imaginary part, which we know is -3. That's going to give me 8. Okay, if you recall, using the imaginary number I, write down an expression for root -9. We can write root -9 as being the square root of 9 times the square root of -1. We know what the square root of 9 is. We know that that's 3. The square root of -1 we know is I. So the square root of negative 9 is 3i. If I have square root of negative 5, that's the same as root 5 times negative root 1, root square root of negative 1. Root 5 we can't simplify, so we leave it as root 5. Negative 1 square rooted, we know is I by the definition. Before we learned that I to the power of 4 was 1, I to the power of 3 was negative I squared was negative 1, and I was I, which is root negative 1. So here, if I have I to the power of 4, we know, like I said before, if we divide it by 4 and see what the remainder is, if we divide 8 by 4, we have 0 remainder. Or I to the power of 4 times I to the power of 4 is I to the 8. It's just 1 times 1, so we get 1. I to the power of 8 is 1. I to the power of 5, if I divide 5 by 4, I end up with 1 remainder. So I get 1 plus I to the power of 1. We don't need to write the power of 1 in there, so we just leave it as 1 plus I. Here with W, we look for our remainder when we divide by 4. So if I divide 6 by 4, I have a remainder of 2. If I divide 4 by 4, I have no remainder. So it's just 3 times 1, because I to the power of 4 is 1. I squared, we know from up here, I squared is negative 1, so I get plus 3 times negative 1, and then I get minus 1. I know that I squared is negative 1, minus 3, minus 3, minus 1, which gives us minus 8. Okay, if I want to find the real part of this complex number, the real part is just the part that doesn't have any I. So in this case it is 5. The imaginary part of 50, well, this doesn't have any imaginary part, so the imaginary part is just 0. In this equation here, I need to rewrite it and simplify it first. So 2 plus I minus 3 times I squared we know is negative 1. So I get that's equal to the real part of 2 plus I minus 3 times minus 1 is plus 3. So that's going to give us the real part of 5 plus I, which in this case the real part of that is just 5. Similarly over here we need to simplify this first. So I'm just going to simplify the top. 1 minus 3i minus I squared minus I cubed. That gives me 1 minus 3i. I squared we know is negative 1, but if I times it by negative I get a plus 1. I cubed we know is negative I, so I get minus I. So we'll end up with 1 plus 1, which is 2, negative 3i minus I, which is minus 4i. And if we put that into this equation, we get an imaginary part of 2 minus 4i on 2, which is the imaginary part of, if I divide them both by 2, I get 1 minus 2i, but the imaginary part of this complex number is just negative 2. With an Argand diagram, it's kind of similar to a Cartesian plane. Instead of having an x-axis, we have our real axis, and instead of having our y-axis, we have our imaginary axis. So our real part tells us how far to go left if it's negative, or right if it's positive, and our imaginary tells us how far to go up if it's positive, or down if it's negative. So here, if I'm looking at the point A, we've had to go 3 in the real direction and 0 in the imaginary direction, so it's just 3. B, we've had to go none in the real direction and 2 in the imaginary direction, so it's 2i. C, we've had to go 4 in the real, negative 4 in the real direction, yes, and up 5 in the imaginary. So it's negative 4 plus 5i. D, we've had to go negative 3 in the real, negative 4 in the imaginary, negative 3 minus 4i. And lastly, E, we've had to go 2 in the real and negative 2 in the imaginary. So 2 minus 2i. If you've covered complex vectors before, complex numbers add and subtract very similarly to vectors. Each component only adds to the like component. So if I've got real component, real component here, we add them together. And if I've got imaginary component, we add them together. So if I was to draw the two, if that was Z1 and that's Z2, if I add Z2 onto Z1 or Z1 onto Z2, we end up at the same spot, just like we would with vectors if I added ij and j components or ij and k components. However, complex numbers is only in 2 dimensions, so you'll only have a real part and imaginary part. As we've said before, if we want to add 2 complex numbers together, we just add their real part and their imaginary part. So z is 5 minus 6i plus w, which is 3 plus 8i. If we add our real part together, we'll get 8. If we add our imaginary part together, we've got negative 6 plus 8, which is plus 2i. If I want z minus w, I have 5 minus 6i minus w, which is 3 plus 8i. We've got 5 minus 3, which is 2. I've got negative 6i minus 8i, which is negative 14i. If I have u minus w plus z, we've got minus w plus z up here, so we can just use that and add u onto it. So I say negative 3 plus 2i, and then plus minus w plus z, which is 2 minus 14i. If we add our real components, we end up with negative 1, and if we add our imaginary components, we end up with negative 12i. If you wanted to, you could have done it the long way. You could have said negative 3 plus 2i minus 3 plus 8i, and then plus 5 minus 6i. We've got negative 3, which is negative 6 plus 5, which is negative 1. We've got 2i minus 8i, which is minus 6i, minus another 6i is minus 12i. Either way, you'll get exactly the same answer. Multiplying a complex number by a constant is the same as multiplying a vector by a scalar value. If it's greater than 1, it'll make it longer by the factor that you're multiplying it by. If it's shorter than 1, it'll make it shorter. So if you multiply it by half, if this was z, if I multiply it by half, it's just going to be a half of z. If I multiply it by 2, it'll be 2z. I just put it next to it. So here, if I've got 2z, I've got 2, 5 minus 6i minus 3w, which is 3 plus 8i. I'm going to end up with 10 minus 12i minus 9 minus 24i. 10 minus 9 is 1 minus 36i. Here we have 5u, and then I've got 5u, I've got minus 3 plus 2w, which is the same as that. So if I say 5u, 5 times negative 3 plus 2i, and then I have minus 3w plus 2z, which we know is this. Sorry, minus 3w plus 2z, minus 3w plus 2z. I can just bring that value over here. So I get plus 1 minus 36i. That's going to give me 5 times negative 3 is negative 15. 5 times 2i is plus 10i. Plus 1 minus 36i. Okay, if we add our real components together, negative 14 and then minus 26i. When we multiply two complex numbers, we just use FOIL as we would with algebra. However, when we multiply two I values together, we know that we're going to get I squared, which gives us negative 1. So here, if I multiply these two together, 5 minus 6i, 3 plus 8i, using FOIL, 5 3s are 15, I'm going to get plus 40i, I'm going to get minus 18i, and then I'll have minus 6 times 8, which is minus 48i squared. We know that I squared is the same as negative 1, so I cross it out and change that to a plus. Then we add our real components together, so I'm going to have 63, and then our imaginary components, 40 minus 18 is 22i, so plus 22i. Here, if I multiply 2 plus 5i by 2 minus 5i, we're going to end up with 2 times 2, which is 4. 2 times negative 5i is negative 10i. 5i times 2 is positive 10i. And then negative 5 times positive 5i is going to give me negative 25i squared. 10i and the 10i cancel each other out because I've got negative 10i and plus 10i. I squared is negative 1, which makes this positive. So we just end up with 29. And I've said here, do you notice anything? It's kind of like rationalizing the denominator. When you want to get rid of a square root, you multiply it by the square root. If I want to get rid of root a on the bottom, I multiply it by root a over root a. Here, we multiply it by, if it's a plus in the middle, we multiply it by something with a negative in the middle. We'll learn more about that later. It's actually called its conjugate. Okay, determine the real part of zw squared and then the imaginary part of z squared w. So let's have a look at zw squared. W squared is going to equal 4 plus I, and then 3 minus I squared, which is going to be 4 plus I. 3 minus I squared is going to be 9, minus 6I, and then plus I squared. We know that that is negative 1. So I'm going to have 4 plus I times 9 minus 1, which is 8 minus 6I. Okay, then when we expand this out, we get 4 times 8, which is 32. I get minus 24I. I get plus 8I. And then I get minus 6I squared. We know that the 6I squared, we'll cross out the I squared and make that positive. Then we add our real and imaginary components. So I've got 32 plus 6, which is 38. And then I've got minus 24 plus 8, which is minus 16i. If I want the real part of that, I want the real part of 38 minus 16i, which is just 38. With z squared w, we know that that's 4 plus I squared, 3 minus I. If I expand out 4 plus I have 16 plus 8I plus I squared times 3 minus I. 16, that's going to be minus 1. So I end up with 15 plus 8I times 3 minus I. 3 times 15 is 45. Minus 15I minus 24, plus 24 is going to be minus 9I. And then I'm going to have minus 8i squared. We know that I squared is -1, so we change it to a positive. We end up with 53, because 45 plus 8 minus 9i. Sorry, I haven't left myself much room. If I want the imaginary part of that, the imaginary part of 53 minus 9i is just the coefficient of I, which is -9. Similarly to when we equate coefficients with algebra, so if I had 3x squared plus 4x plus 10 was equal to ax squared plus bx plus c, we know that a must equal 3, b must equal 4, and c must equal 10, because our coefficient of x squared equals our coefficient of x squared, and so on. Here, if I've got 4 minus 3i is equal to 2a plus bi, we know that 2a has to equal 4, therefore a has to equal 2, and we know that -3, my coefficient of I, has to equal b. So my two answers are a equals 2, b equals -3, and that satisfies this equation up here. Similarly here, I've got 2a plus 3b has to equal -1, and I have a minus 2b has to equal 3, the coefficient of I. Okay, with our equations here, I'm going to multiply the second one by 2, so I'm going to get 2a minus 4b equals 6. Let's call that equation 1 and equation 2. If I let's use 1 take away 2, 1 subtract 2, 2a take away 2a cancels, 3b subtract minus 4b is 7b, -1 take away 6 is -7, b equals -1. Sub that back into, let's put into the first equation, 2a minus 3, because b equals 1, is -1. 2a is equal to 2, a is equal to 1. Therefore our solution is a equals 1, just did that, and b equals -1. Over here we've got our real part, so a plus 2b is equal to 7, and we've got our imaginary part, -3ab is equal to -15, so I'm going to say 3ab is equal to 15, make them both positive. Okay, from here we can get, let's get a by itself. A equals 5 on b. When I divide that to the other side, if we sub that into this equation, we get 5 on b plus 2b. So if I put that into equation 1, sorry, I should have written 1 and 2. Okay, I get 5 on b plus 2b equals 7. Multiply everything through by b. So I get 5 plus 2b squared minus 7b equals 0. I just brought the 7 across the other side and multiplied it by b. I'm going to end up with 2b squared minus 7b plus 5 equals 0. Let's bring it up here. Okay, what does that factorize? 2b b equals 0. I want to end up with 2 times 5 will give us 10. That's no good. 2 times 1 is 2. And then 5 will give us 7. They both have to be negative because I want to end up with a negative in the middle. 2b squared minus 2b minus 5b is minus 7b, and then plus 5. Therefore we get b equals 5 on 2, or 1. Okay, if we know what b is, we sub that back into this one because it's easiest. B equals 5 on 2. A is equal to 5 divided by 5 on 2, is the same as 5 times 2 on 5, which is just 2. And if I put 1 back into that equation, b equals 1, a equals, put 1 into there for b, I just get a equals 5. So they're my two solutions to this equation, which will make them equal. Okay, there's something significant that happens when we multiply a complex number by a negative, or by a negative I, or by a positive I. If we multiply a complex number by -1, if you think about it, if I had 2 plus 3i, if I was to put that in the complex plane, I would go across 2 and up 3. So there's my complex number. If I multiply it by a negative, I get 2 plus 3i, which is -2 minus 3i. So if I go -2 and minus 3i, it's going to bring me down here, which is significant because it's 180 degrees. So like with a vector, if you want to turn it around or make it go in the opposite direction, you multiply it by a negative. If I use the same vector, the same complex number, 2 plus 3i, if I multiply it by I, we will end up with 2i plus 3i squared. But we know that 3i squared, I squared is -1, so we can replace that with a -1. I end up with -3 plus 2i. So if I go across 3 and up 2i, that will bring me to here, and it actually results in rotating at 90 degrees in an anti-clockwise direction. So we want to rotate a complex number about the origin. If we multiply it by I, it will rotate it 90 degrees anti-clockwise. If we multiply it by -I, and you can have a look, -I times 2 plus 3i, we know that's -2i, and then minus 3i squared. That's going to give us a positive there, so 3 minus 2i. If I go across 3 and down 2i, that has a result of rotating it 90 degrees still, but this time in a clockwise direction.